Alrighty, let's continue our adventure in terms of solving trigonometric equations. And this time we're going to be actually really getting into the meat and potatoes, which is that there are an infinite number of solutions, okay? So we're going to look at two different ways we can represent the infinite number of solutions. Now you can see that this question looks almost identical to the last ones we were looking at, except this time we've got a 2x inside the parentheses. So instead of solving for x, 2x, let's just solve for, say, theta. So let's just rewrite this. Let's say theta is equal to 2x, and now let's just make this cos of theta equals a half. Okay. Well, that's a lot easier to do. So let's just write a reference triangle. Now we're going to need the 1, 2, root 3 triangle for this one. And I love to put the 2 and the root 3 in the wrong spot. Alrighty. And we're working in radians, as you can see by the domain. So I'll put in the radian equivalent angles. Alrighty, so what is it going to be? Well, we need this to be the adjacent and this to be the hypotenuse. Well, that means this must be our reference angle. We do want it to be positive, so looking back at our unit circle, we're going to have two reference angles. The two reference angles are going to be in the first and the fourth quadrant. The all and the cos one, because we want cos to be positive. So let's draw in that pi on 3 angle. Cool. And that's looking just lovely. Okay? So we've got two solutions, two base solutions, right? So either theta could be equal to pi on 3 plus or minus 2 pi n, for n in some double z. And our second solution, well, that's going to be, so that's theta 1, let's say theta 2 is going to be, well, the exact same, except we're going to be, it's 2 pi minus pi on 3 plus 2 pi n. Or let's say 2 pi m for m in some integers, okay? So these are our two families. 2 pi minus pi on 3, the parentheses here are just for working out this angle going to here. And so it's going to be 5 pi on 3. Those are our two basic solutions. Okay, so rather than just talking about it, let's actually write down some of the infinite solutions, okay? It's going to be important because, remember, we're not actually solving for theta, we're actually solving for 2x. And so we're going to need to make this substitution at some point. So let's say theta 1, well, that's equal to a set of numbers, pi on 3, and then plus 2 pi. But adding 2 pi is a bit of a pain, so let's instead add 6 pi on 3, which is still 2 pi, just written a little bit easier. So this is going to be 7 pi on 3. And repeat again. The next one is going to be 13 pi on 3. And the next one's going to be plus 6 again, is going to be 19 pi on 3. So you can kind of see there's a little pattern going on here. I could even go backwards as well. If I wanted to go minus 6 pi on 3, well, that's going to get me to negative 5 pi on 3. But remember, there's an infinite number of solutions either way. This is a sequence of solutions. Okay. Except, remember, I wasn't ever actually trying to solve for theta. I was trying to solve for 2x. So let's replace theta with 2x now. Okay. Now what I want to do is I want to move the 2 to the other side. So I want to divide everything by 2. So let's do that. And I'm still going to put a 1 because, remember, I've still got to do this for theta 2. So x, after I divide by 2. So I'm going to divide every single thing on this side by 2, right? I'm going to divide all of them by 2. The way that works is that when you divide, it's going to join the bottom. So basically all of these are going to become ... minus 5 pi on 6, pi on 6, 7 pi on 6, 13 pi on 6, and 19 pi on 6. Okay, so those are now all my different values going on forever. Right? That's one family. The question is, which ones of these fellas are within this domain? I need to check all of these ones and see which ones are in between that. Now, this guy's out because it's negative, and the smallest number we're allowing is 0. So the first legal one is going to be pi on 6. Question is, when do we get past 2 pi? Well, once again, it's useful to write 2 pi instead of as 2 pi, but as sixths. So let's make this 12 pi on 6 is what 2 pi is equal to. So we don't want anything bigger than that. So you can see there's only two solutions in here, pi on 6 and 7 pi on 6. 13 pi on 6 is too big. So we're going to ignore those guys because they're too big, and we're going to ignore that guy because it's too small. Okay? So those are our first two solutions. Now we're going to repeat all of this, but for theta 2. So once again, let's write out the family of values for theta 2. So we get 5 pi on 3. And again, we could add 6 pi on 3 either direction to get a new solution. So plus 6 pi on 3. And that's going to give us, say for example, 11 pi on 3. And then the next value would be 17 pi on 3. Dot, dot, dot. Okay? And then going the other way, we would do the exact same thing. So I'd get minus pi on 3, and then so on and so forth, right? So we can just add or subtract 6 pi on 3. And notice that really the only thing that's changing is the numerator, the coefficient in front of the numerator of pi. So basically it's 5, 11, 17, and then negative 1 would be the first one going the other direction. Okay, so it's really important to be able to see those sorts of patterns. But once again, we weren't ever trying to solve for theta 2, so let's replace theta 2 back with 2x. And this is going to be x2, because we're now solving for the second group. And so x2 is then going to be, well, divide everything by 2, minus pi on 6, 5 pi on 6, 11 pi on 6, and 17 pi on 6. Okay? So I've now divided everything by that, and now I just need to see which are the ones that are within the range. Remember, the domain was 0 to 2 pi, and we worked out 2 pi was 12 pi on 6. So this one's too small. 5 pi on 6 is good. 11 pi on 6 is good. 17 pi on 6, too big. Okay, so we've only got two solutions from this group, 4 solutions in total. So in total, x is equal to the set of numbers pi on 6, 7 pi on 6, 5 pi on 6, and 11 pi on 6. Those are the 4 solutions to that equation. Let's repeat it, but this time with some addition and subtraction. Once again, we're still solving between 0 and 2 pi. Alrighty, so once again, make a substitution. So let's say this is just equal to theta. So we're saying theta is equal to x minus pi on 6. Just clear substitution. Alrighty, we're looking for negative a half. Once again, this is the triangle we're going to need. And we're still working in radians. That needs to be opposite, that needs to be the hypotenuse, so that means this needs to be the angle. So there's our reference angle, except we're dealing with negatives. So when we're dealing with negatives, right, we need to be finding the not sine quadrants. So which are the not sine quadrants? This one and this one. So let's draw in our angles, and it's going to be pi on 6, so pi on 6 here, and pi on 6 over here. Alrighty, so this is going to be our 2 families of angles that we're going to be looking for. So they're both starting like that. So let's work out what each of these angles are. So the first angle here, that's going to be pi plus pi on 6. So our first reference angle, theta 1, is going to be 7 pi on 6 plus 2 pi n, for some n in some integers. And theta 2 is going to be, well, nearly a full rotate. Oh, let me change colors. Theta 2 is going to be equal to 11 pi on 6 plus 2 pi m for m in the integers. Remember, when I say integers, integers means whole numbers. So -2, -1, 0, 1, 2, 3, 4, 5. Okay, so now let's actually go through and work out the numbers within these sets, okay? So once again, let's go through. So let's start off with theta 1. So theta 1 is the set of numbers starting with 7 pi on 6, going plus 2 pi, but I'm not going to actually add 2 pi because that's hard. Let's add 12 pi on 6. So it's going to give me 15 pi on 6, and then 27 pi on 6. And then going the other way, it's going to be -5 pi on 6, and ... Okay? So these are all of our solutions so far. But again, we weren't ever trying to solve for theta. We were actually trying to solve for x minus pi on 6. So what am I going to do to both sides? Well, I'm going to add pi on 6 to both sides. So this is now -4 pi on 6. This is now 8 pi on 6. The next one is now 16 pi on 6. And the next one is 28 pi on 6. Except you'll notice all of those have even numerators and denominators, so I can actually simplify them into thirds. So once I simplify this set, I get -2 pi on 3, 4 pi on 3, 8 pi on 3, and 14 pi on 3. Alrighty, so these are my infinite family for the first one. Now I need to see which ones are in between 0 and 2 pi. So we worked out before that it needed to be between 0 and 12 pi on 6. We're working in thirds now, so it should be over 6 pi on 3. So that's our only solution. Right? Because 12 pi on 6 is equivalent to 6 pi on 3. So 0 to 6 pi on 3. So there's only one solution in the first set. So x1 gives us only one solution. Let's do x2 now. So x2 minus pi on 6, that's going to be based on our theta 2 one. So starting with 11 pi on 6. Same game, plus 12 pi on 6. So adding 12 pi on 6, so adding 12 pi on 6 is going to give us 23 pi on 6, which I think is definitely going to be too big. So I'm going to stop there. And going backwards, we're going to get -pi on 6. And subtracting another one will give me too many. So now we're going to add pi on 6 to both sides. Alrighty, well, minus pi on 6 plus pi on 6 is 0. That's going to be 12 pi on 6, which simplifies down to 2 pi. And the next one is going to be 24 pi on 6, which simplifies down to 4 pi. So this is my new family of solutions. Which ones lie between 0 and 2 pi? Well, 0 and 2 pi do. So in this case, we actually have 3 solutions. So x is equal to the set 0, 2 pi, and 4 pi on 3. And that's it. Just those 3. Because again, in reality, we have an infinite number of solutions, which is what these guys represent, the infinite family. But we're only interested in the ones between 0 and 2 pi. Alrighty, I'll see you in the next one. Goodbye.